then you see a drop. But technically, when you have 23% carbide content, your drop occurs at much more earlier cycles. So basically, as soon as you start, your friction is low. So that's why I call that coating as a kind of Superman coating, because it actually gave us less friction. And then what we did next is, like, then you see a drop. The load, but we thought, like, what happens if we increase the load? Like, if my component suddenly subjected to more load, what happens? So in case of at higher loads, our Superman coating, that is 23% TIC, is still giving low friction. In fact, friction came down actually slightly, whereas the other coatings didn't perform that well. So which means that if you want to go for an application, it's better to go with 23% titanium carbide, where if you need low friction, so based on that, you need to choose your coating. The next slide. So once the friction was measured during the test, next part was to wear. So here you can see at both loads, at half Newton load, you see a decrease in wear rate also. So you see that titanium 64, the wear rate is around 196 into 10 power minus 7 cube per Newton meter. Whereas when you compare our composites, that is 16% and 23%, they are at least 8 times less wearing. And in fact, our 23% titanium carbide coating, the wear actually has come down by 10 times. So we are technically saving our material, and also we are improving its wear, and also we are getting low friction also. Yeah. Even at 2.5 Newton normal load, our 23% titanium carbide TIC was a best performance coating, which actually gave extremely low wear rate. You can see when you compare with our base coating, that is titanium 64 itself, your composite almost wore 10 times less. So that's the advantage of actually incorporating titanium carbide particles into the matrix itself. Here with the next slide. Yeah, so this is basically the comparison I'm showing, that is 16%. There's slight increase in wear rate at 2.5, which we'll know why next. But our 23% coating, the wear rate is extremely low. So you can see that even if you increase load, there's very marginal increase in your wear rate. So next, once we have the result, the next is to understand the science behind why we are getting this. So when you see your wear track, in case of titanium 64, you basically have the plowing marks. So that's because the wear debris that are formed, the particles that are formed, they are basically scratching your surface. So that's why you have those high friction points, because basically those hard particles are actually scratching during the wear process itself. Next. And when we did some Raman microscopy analysis, we found that those particles are actually titanium oxide particles. So once you have an oxide coverage, because when actually the components subjected to air, you have oxidation, and then you have oxide particle formation, fragmentation, and then you have wear of the coating itself. So that's why basically you have a lot of wear on the particle, because these hard particles are actually abrading the surface. Next. Yeah. So now if you see one more, yeah. So now if you see that in case of titanium 64 TSE MMCs, so the left side where you can see that on the wear track, when you have carbide particles, you don't see such kind of groove marks, but you see there is a protective layer that is being formed. If you can see the left side image, top image, you have those islands of tribo layers, we call basically, because they're agglomerated oxide particles. So once you have those titanium carbide particles, actually it stabilizes your wear process, and then you have this protected layer formation. So once you have this protective layer, you're not exposing the subsurface. So these protective layers were not formed in case of pure titanium 64 coating. And when you increase the titanium carbide content, that is 23%, these layers are more continuous on the wear track, which means that your titanium carbide particles are basically facilitating for the formation of these hard tribofilms. And when we did Raman analysis on these tribofilms, actually, we found that apart from titanium oxide and carbide, we could see free carbon. So that free carbon was basically the free carbon that we had in the particle. So what is the advantage of free carbon? Can you go to the next slide? Yeah, so that was the free carbon what we saw in the initial particle itself. So this carbon was coming up onto the wear track, and then once this carbon was coming up, it's a graphitic carbon. Since graphite has layered like structure, so it is giving actually lubrication, and then due to which it's kind of a solid lubricant, and due to which you are seeing the drop in coefficient of friction. So the drop, what we had seen during the wear test was basically you are wearing initially, that's because you are seeing similar friction. And then once you're wearing out, these carbide particles are getting exposed to your wear track, and there's solid lubrication, formation of layers. That's where your friction and wear are coming down. So that's the science behind the why it's coming down. Next. So that's what I explained. As I explained, so once you have these tribo layers, and with these layers containing free carbon, so this carbon is actually bringing down the coefficient of friction after the test started running, and that's why your friction is coming to 0.3. So it's kind of a solid lubricating process. Next slide. Yeah. Even at 2.5 Newton, when we increase the normal load, we could see one slide back. Yeah, thanks. So when you see in case of titanium 64 and our composite with small less carbide particles, so you see you still have abrasion process. That is the sliding marks you can see on the top images. So that's why at 2.5, even if you have 16% titanium carbide, you're not seeing tribo layers. But when you come down to the bottom image, where you have 23% carbide, you could see there's a continuous strip that is formed. So that's basically the wear track. So which means that the ball that was sliding is not interacting with the subsurface. It's only interacting with those layers. So that layer is like a protective layer on top, and the ball is moving on that. So that's why you don't see those friction rises. You see a drop in friction, and there's also carbon, so which is further assisting its wear resistance. Next. Yeah, so that's why you're seeing a friction drop in 23. As you can see that in the blue curve, that is our 23% titanium carbide coating. So you see a drop, it's actually going to 0.25. So that's because initially you wear, but then you form these layers. As soon as you form these layers, you see a drop, and then it goes from there. Next. So next was basically to see the subsurface. This is a bit complicated to understand and explain, but just to give a brief outline. So we cut the wear track. So if you see the left side, basically the image. So basically it's a wear track cross section. So the arc what you see is basically a wear track. So once you cut it, you could see that you have a, yeah. So that red color is basically box is basically your tribofilm. So in that tribofilm, if you start matching your elements in the down, you could see oxygen and also those small particles. Yeah. So that was oxygen map. So second one is small particles. That the small particles were basically carbide particles. So inside the tribo layers, those small particles are fragmented particles. So you can imagine this like a cake with cherries inside it. So cake is soft, so the matrix is soft, and the cherries are considerably bit hard, right? So that cherry is basically your carbide particle. So that's the composite effect what you're getting. You have something which is taking more stress and also improving its hardness. So that's why you don't lose the wear, you get the wear resistance. So that layer, what you can see, is formed on top of the composite wear track. So that layer actually prevents your base material wear out during actual application. Go to the next slide. Yeah. So below the wear track, you could have some amount of deformation because some kind of stress might go, but you don't see some sharp changes in microstructure itself. So which means that you're actually protecting your subsurface also by forming these type of films. How we concluded this? Next slide. So yeah, one more. So we did indentation on the wear track cross section itself. So the left side cartoon is basically the triangles are indent marks. So it's the yeah. So that's the indent marks. So those indents are basically the Vickers indents. So we did Vickers nano indents. So those are very small indents. So they fall at different places. So then we correlate this hardness where the indent fell. So that's region's hardness. So if you see the right side graph, so here basically you could see that at the tribolayer hardness is basically very hard actually. So which I marked it. So you can see that the near surface hardness when you have these tribofilms is very hard. It's around 8 GPa. But in case of titanium 64, there's a blue fellow down there. Titanium 64, the red and the blue guys, your hardness is very less. So sorry, red and black. So the titanium 64, your hardness is very less. So when you have tribolayer formation in composite, basically you are having very high strength at the surface. You wear less, but when you don't form tribolayers, basically you actually wear out faster. So that's how we concluded that when you have tribolayers, you're basically improving the near surface hardness of your material. So as a result, the material that is getting exposed to your actual severe wear conditions is getting less worn out. So even though if you have a small material there, you are actually prevented a bulk surface. So that's one application what we found. Next. So this is some interesting microscopy we did. This is a transmission electron microscopy. So what we did basically was, yeah. So what we did basically was we cut the wear track. There's a fib cut. So basically you cut it with electron beam. And how we cut it, that's actually the red mark on the left side image is basically the location where we perform this cut. Yeah. So that's the darker contrast there is basically your tribolayer, and the lighter contrast is basically the well track itself. Yeah. So why we cut it this way? Because in a single cut, we wanted to see how is the microstructure below the tribolayer and also away from the tribolayer. So on the middle image, if you can see, so the cut and then we rotated it and then we saw in the microscope. Yeah. So there you can see the below tribal layer, your grains are a bit larger. So technically, if your grains are larger, you have less deformation. Yeah. In the blue image, where the mouse is pointed out, so that is under the wear track, which is not covered with tribal layer. There you have highly refined grains. So which means that when you don't have tribolayer formation, your subsurface is getting highly deformed, due to which you have very fine grain formation. Whereas when you have, yes, that's the location where the mouse is pointed out. There you have extremely high deformation because you have no tribolayer coverage. On the top image, just above it, the red color one, yeah, where you have tribolayer, your grains are actually bigger. So that's why your deformation is less, which means that when you have tribolayer formation, you are actually getting less stress transferred to base material. So your base component is less stressed when compared to location where you don't have tribolayer. So we need to promote this tribolayer formation during wear. So that's something open question what we have is like how we can further increase this tribolayer formation or area coverage on the wear track and try to get maximum wear resistance. Next slide. So just to summarize the wear mechanisms, what I explained till now, in case of titanium 64, you have a coating. So you have the tungsten carbide ball, and then, yeah, so that's the initial test condition what we start with. When you go to the next condition, in the right side, yeah, you have transfer film, that is material goes into the wear track. You have formation of wear debris, which were titanium oxide particles on the right side extreme image, where those oxide particles basically abrade your surface, and there you don't have any protective layer formation. That's why you keep increasing your wear rate and also your friction. Now when you come to the composites, that's a down image, there you have titanium 64 matrix, and then you have small particles that are embedded inside that, and then when you wear out, you start exposing these particles, and once they stabilize, then you have formation of tribal layers. That is the extreme image, yes. So that's the tribal layer formation, and once you have tribal layer formation, you don't wear out your material. So that's the advantage of having a composite coating on your part rather than having a metallic coating. Next. So we did some high temperature tribology because I won't go into too much details. So I just present like overview what we did. So this study was carried out in collaboration with University of North Texas. So this is actually high temperature study. So where we expose our coatings to extremely high temperature, that's around 600 degrees centigrade, we could expose, and we do the wear test at that particular temperature. So that's a line diagram. So there you have a heating coil. Though there you have a heating coil, and then you have a rotating stage on top of it, and then you keep your specimen, and there is a thermocouple. So you set your temperature using a temperature controller. So you can put a temperature, so it heats and cools actually, basically. So it controls your temperature. So you wait, and there's a heat shield. So the entire one goes into a heat shield. So so it's a heat shield. So then you cover it so that you don't have heat loss that much, and then you do the test. So what test we did at room temperature, we did at high temperature also. So same condition we use pretty much, and then it's a slightly different setup because of a different laboratory. So but it's same sliding. So we say similarly recorded a friction and wear rate. Can you go to the next slide? Yeah. So here's a wear rate. So I won't show friction because we didn't find that interesting. But even at high temperatures, my composite coating, composite I mean the 23% titanium carbide or Superman coating, so actually wore less when compared to metal coating, that's a blue colors, at all conditions. So at room temperature 200, 400, and 575, that is close to 600, our coating was very wear resistant. We had extremely less coating. Can we go one slide? Yeah. So those green arrow marks are basically our composite coatings we specify, and the blue ones are basically the metal coating. So when you have composite coating, it wears less. And secondly, if you see at 400 and 575, the counterface wore basically. The coating was highly protective. So which means that at higher temperatures, our wear resistance is pretty much improving. And also, when compared to pure Ti64, at all temperatures, the composite coating is performing better. So I won't go into the results because it's very complicated analysis, but we have a paper published, so the reference is down. So if you're interested, you could always go into for more details. So we go to the next slide. Yeah. So this is basically our my overall research, what I did for my PhD. So there are other composites also that were being sprayed in our research group, by my colleagues. So the website down, I put a hyperlink, is basically our research group, the www.msectl.com. So there, if you can copy and see, there you have list of all papers what we published and what all my colleagues published. So some coatings. Oops, can we go back? Yeah, thanks. So some coatings which we studied by my colleagues include nickel tungsten carbide composite coating. So it's for high wear resistance applications, mining equipment, construction trucks, that's drilling and digging equipments. We have some alumina composite coating we studied that was mostly for aerospace and automobile applications. There was also copper MOS2, copper molybdenum disulfide. Molybdenum disulfide is a solid lubricant like graphite. So this is basically used for outer space applications because you can't carry a liquid lubricant there. It's very dangerous. You have leaking problems, then you have other issues. So they use solid lubricants. So one of my colleagues studied copper MOS2 composite coatings. It's a self-lubricating composite for aerospace applications. And she also studied hybrid composite, which is copper tungsten carbide MOS2, that is molybdenum disulfide, which actually gave a composite effect, that is, you get both high wear resistance and also low friction. So in the hybrid composite. In case of copper MOS2, there was mostly low friction only. Next. So future directions, what is still studied in this thermal spray or in this cold spray process, that we still need to understand how the particle is interacting with the gas spray and start predicting the variables, how they change, because we can't do every experiment. So that's where simulations are being widely used. We have a close collaboration with other groups who are doing finite element simulations and CFD simulations to actually mimic the inside the nozzle, and also nozzle design is something which is being widely studied because we are studying the material aspect. There's also the mechanical aspect where they want to see how we change the nozzle parameters, you start getting better coatings. And then one more other thing is, since the input is the feedstock, so you need to understand like how different powder fabrication techniques lead to different physical, chemical, and mechanical properties. So that's basically where I emphasize that process, structure, property, and performance correlationship. So it's a chain. So we need to understand more about the powders itself. And then FEA simulations are being extensively carried because one still problem is we are not able to retain all ceramic particles when we spray. For example, I could retain only 23% out of 50, which is around 46% only. So the efficiency is around 46 only. So they're trying to simulate these conditions to see what things we can do to potentially improve the ceramic retentions. So once they come up with some conditions, we can do minimal experiments and come up with a solution. And recently, since cold spray is a heat sensitive process, I mean, it's to mean say that substrate is less exposed to temperature, to harsh temperatures. So they are trying to deposit metal coatings on polymer substrates. So that is mostly for aircraft applications. I think Airbus is trying to do for their A330 Boeing aircrafts that when you have polymers, so can we have metal coatings? So that's something which is being widely studied now. So these are future directions. Can we go to the next slide? Yeah. So I would like to end. I thank my research supervisor, Professor Richard Kromick. So that's my group image. That's pretty old one. So as in 2016 when I joined the group. So it was a cold winter in Canada. So we are all in the big coats. So the person standing right in the front is my research supervisor. So he's Professor Richard Kromick. Yeah. So and then I thank him, and then I thank my colleagues, both at National Research Council of Canada and also my research group and my fellowships that helped me to supported my research financially, and all our generous sponsors who have been really supportive in giving us all the feedback and raw materials, etc. And thank you for your attention. Next slide. Yeah, thank you for your attention. And if you have any questions, I'm happy to take them.
Thank you, Dr. Venki. I
Thank you.
request the participants to post their questions in the chat box if you have any, sir.
Okay, I'll just try to see.
I think Dr. Vamsi, questions, none of the questions are there.
I think so. There's one question by Becha Ravi Kumar. So,
Yeah.
sir, so I think can 3D printing technology be adopted for cold spraying? Yes. What happens is basically cold spray is seen as an additive manufacturing process. So, but the problem is, as per ASTM standards, you have 7 process that is listed as additive manufacturing, and cold spray is not listed there. That's why people sometimes don't consider cold spray as additive manufacturing and 3D printing technology. But I think that's just because of some politics or something. So, but people say it's cold spray additive manufacturing. So, additive manufacturing fundamental definition, if you look at something which you are adding layer by layer is additive, and something if suppose you're machining, it's subtractive.
on behalf of the team.
So,
We have one more question, sir, from LNK Dharnija.
yeah, yes, I'll just. Okay. Will hot spraying create a more efficient triboloer with more graphite compared to cold spraying? Yeah. There is something called warm spraying. So you could try that. But the problem is that you need to understand that if there are too many phase transformations, you might lose the mechanical strength of the material. So we need to see hot spraying, what temperature the particle is getting experienced,
Yes.
and the process itself won't give tribolayer because tribolayer is formed during wear. So it's kind like how much ceramic particles you retain. If by hot spraying you are retaining more ceramic particles, of course it is beneficial because you might form a tribolayer at much early cycles, or maybe you form a tribolayer over an entire wear track, not only islands. So in that case, we actually go for warm spraying. Yes, that's completely there. But then we need to understand that if you're doing too hot spraying, what is your substrate? So if you are creating some problem with the substrate, then it's a problem because when you bring back a component from where worn component, you don't want to lose the substrate mechanical strength. So I hope that answers your question. Any other questions? If you have, please feel free to ask.
I think Nirvik Chaudhary has one question. Do we have some same defects in cold spray similar as 3D printing?
I'm not an expert in 3D printing, so I don't know what kind of defects they experience. I think in 3D printing, it's mostly, if I know correctly, there's a big group that's working on additive manufacturing. They have mostly phase transformations. So you basically melt the particle. So they what they report is they have heat affected zone, HAZ. So like what you have in welding. So that heat affected zone is basically the weakest link actually. So that's where your crack can start. So you need to check for that particular material if AM is a good process or that's additive manufacturing, or if you have cold spray is the best process. Yeah, it depends upon your application. Yeah. And I think we have one question from Obul Reddy. So he says, okay, for aerospace supersonic vehicles, which type of spray coating is useful to decrease the heat generation on surface of supersonic vehicles? You need to check because you need to check the thermal conductivity. So that's the principle they use in thermal barrier coatings. When you have TBCs on the top, they use yttria stabilized zirconia. So the function of yttria is basically the thermal conductivity aspect. Cold spray you could try, but you need to understand that every process has some limitation. So if your material is giving you a very dense coating, so then it's good. If you are losing your mechanical strength because it's a mechanical and metallurgical bond, then it's not advisable because at that particular application, you might lose the mechanical strength of the material and then you may end up having some crack or something. So we need to check. So any other questions?
I think these are the questions, Dr. Vamsi. I request Suman Raj to give the vote of thanks.
Okay, thank you, sir.
Yeah.
Good morning, one and all. Myself, V. Suman Raju, Assistant Professor, Department of Mechanical Engineering. On behalf of Team ATS and FF, first, we proud of you as a alumni of MVSR Engineering College. Uh, Now, I would like to thank today resource person, Dr. Emian Vamshi, for the enlightening presentation to us. Thanks for your valued time. Even though midnight in Canada, your location, so spend valuable time. Thanks for your patience and thanks for the readily accepted our request and thanks for your clarification on today presentation thermal spray coating on automobile and aerospace components. Thank you very much. Thank you very much. Over to Yogi.
Vamsi, it's pride, Vamsi, 1 minute. It's
Okay.
pride and privilege for us, Dr. Emi and Vamsi, to have you on board. The moment we have asked you, you have just accepted it. Last 3-4 years, your international awards are the actual achievements what you made it to the world. And I really, from the bottom of heart, the management, principal, staff, and students, wish you a wonderful success in the coming years. And thank you very much. Being midnight, I think it's almost 1 o'clock in Canada. Being midnight, you were attentive from 8 o'clock Indian time. Thank you very much, Dr. Vansi. We'll be seeing you forward to have a wonderful association with you in the coming days. Thank you very much.
Thank thank you very much for your for giving me this opportunity, and I would like to especially thank Ravi Kumar sir for patiently navigating through the slides. So he I think he helped me a lot, like pointing to the right place where I wanted to say. So thank you very much, and hope I see you all in future. Thank you.
Thank you. Thank you. Over to Yogi Man.
Oh, thank you, sir. Good morning, participants. Well, I'm happy to introduce Sharma sir to the participants. Dr. G. Srinivas Sharma sir, we call him Sharma sir, was graduated from Bapatla Engineering College in the year 1993 with specialization in mechanical engineering. Obtained his postgraduate degree, MTech, from College of Engineering Anantapur. It is now called as JNTU Anantapur in the year 1994, and has obtained PhD from Osmania University in the area of biomass gasification recently. And his areas of interest are combustion, heat transfer, gasification, aerothermal heating, fluids, and artificial intelligence. Worked as a graduate engineer trainee at Voltas for short time in 1993 and 94, and started the career as lecturer at MVSR in the year 1994. Presently working as associate professor at our college, MVSR. He also took abroad assignments and worked as system analyst at MK Universal, a Texas-based company, and developed commercial code for Intel Corporation at Portland in nanometrology. He has authored about 20 technical papers, and um, he is an active member of Society of Automotive Engineers and Indian Combustion Society. Well, I'm happy to share this thing. He is the person behind the establishment of Renewable Energy Club of MVSREC and successful conduct of Akshay Urja, a biennial event which is most loved and cherished by our students. Students like him a lot and shares a special bond with him. Uh, Received Best Teacher Award 3 times at our college, MVSREC, and conferred with Lifetime Best Teacher Award by Matrusri Educational Society, under which our college comes. Also awarded by Cognitive Technology Solution as Best Teacher for the year 2014-15. Recently awarded with Best Paper in International Conference at NIT Rourkela. He loves to play cricket and develop algorithms for artificial intelligence and also machine learning using Python. You have always been a great source of inspiration for us, sir. Eager to hear your presentation, sir. Over to you, sir. Screen is all yours. Thank you, sir.
Thank you, dear participants. I'm G. Srinivas Sharma, Associate Professor at Department of Mechanical Engineering, MVSR Engineering College. I take the privilege of presenting a topic on integrated gasification, combined cycle analysis, where we are trying to look at fuel cell technologies associated with combined cycles. Let me present my presentation.
You can present, sir.
Yeah. Can you see my screen, please? Yeah. Can you see the screen? Hello? Hello? Hello?
Yes.
Yeah. Yeah. So the topic of today's speak for next coming 1 hour is integrated gasification combined cycle power plants trigeneration concepts. This is one particular thing where world is looking around. World is looking around at generating more amount of power to the given inputs. So here we are trying to look at gasification as one particular aspect of combined cycle power plants. My topic is planned for 5 particular phases. One is the global scenario and future energy requirements. Second is a gasification phase. Third is integrated gasification combined cycles. Scope of medical in integrated gasification fuel cell technologies, and IBGFC modal issues. What are the issues we are facing as on now? If we look at the first phase, the very first phase, we talk about future energy demands. In the world energy scenario, as per 2013 records of Energy International Association, International Energy Outlook, where you have seen this particular source, it says that there is a gradual increase in the energy demand. And as thermal engineers or people looking from the standpoint of power plant operations, we have to be very careful, and we should not live in the present situation of thermal power plants. Rather, we have to look at around 20, 30 years right down the line from now. Right, something like we are thermal engineers working in power plants are mostly forecasting engineers. So if you look at it in 1990, these are the requirements. And 2010, if you observe it, this blue is indicating oil. This is coal demand. Then comes your natural gas, methane. Then you have renewables and then nuclear. If you observe renewables and nuclear, their fraction is very, very less. But we still, always move into it. But standpoint from fossil fuels, oil, coal, as well as natural gas, they always take the major share. The lion's share is always from the state of fossil fuels. And if you observe it, this is a prediction. This is your energy independence document. Even published by Government of India, when Dr. APJ Abdul Kalam was the president of India. He has envisaged what we have to be at 2020 and what we have to be there at 2040 and odd. And but I took the stats from the international energy organizations, and then at 2040, this is our requirement. There is a huge requirement. Oil requirement may be coming down. Coal requirements. You observe gradually that there would be a slight increase in nuclear as well as renewables, but 23% in 2014 is definitely higher than 22.3% in 2010 or 21.2% in 1990s. As per the estimate, the energy stats, generally we have to be very careful with energy stats. Energy statistics, whatever that has been published, we have to be very careful with the source of publications. And if you observe it, there is a growth. The world would require 56% more energy in 2040 than in 2010. Or if you observe it, maybe at 2020, this is where we are. This is 2020, this is 2030, and this is 2040. And if you look at 2020, from 2020 onwards to 2040, because we are here now. From 2020 to 2040 onwards, 2040 onwards, it may be more around 36 to 40%. Because already we took that gradient from 2010 to 2020. So if you subtract from this 56%, maybe around 36 to 40% would be the steep rise. And that's alarming. Why? Why it is alarming? If I can go back and present in my next slide, this is always bothering me. Whenever I talk thermodynamics, I talk applied thermodynamics, so I talk about thermal engineering. Anywhere we talk about energy, and we always say fossil fuels, they deplete. And if you observe this annual production growth rate is put on the x-axis, and on y-axis date at which the proven reserves are depleted. And these particular depletion reserves are based on the estimates from the mining departments, the estimates from the geological survey, World Geological Surveys. And what it says is, say suppose this blue line is indicating oil reserves, this red line is indicating the natural gas, and the black line is indicating the coal. Now, as on now, our growth rate, that means, whatever the production rate of your oil, coal, or natural gas, you keep it as is. Say, suppose, as of now, India has a coal mining rate of around 46%. Generally, whatever coal reserves we have, we are digging out around 46%. That's one simple estimate from national coal mines. And if you look at it, if you go at the same rate, the coal will last up to 2130 or around 2120 to 2130 in between. This is. And so suppose our oil and natural gas, what you are taking up, your oil will last up to 2055 and natural gas up to 2070. And beyond which, don't know. So suppose I go with growth rates. I go with a growth rate of, say, suppose 1% increase in the growth rate of your oil production. Say, suppose this. So if I have increased my oil production rate by 1%, instead of depletion by 2055, it's getting depleted by 2046. And so suppose if I try to go at a annual production growth rate of 8% per annum, you observe clearly that oil is gone. Oil is gone from 2030 to 2040. This is one point which is bugging most of the automobile industry. And per se, forget about automobile industry. Power plants, most of the power plants will be deprived of oil. And this is alarming. I'm telling you, this is one point where we have to be careful, because my earlier slide is indicating the requirement for demand, and my next slide is saying that my reserves are getting up. I have very bad inventory, and then I can't order it on Amazon to get back oil, natural gas, or coal. That's for sure. So what would be the other option? There should be some option for me. So what should be the other option for me? For now, either we have to reduce your annual production growth rate, which will decrease your economic index, because most of the countries which are saying that they are developed countries, they have a huge amount of energy index. As far as my understanding goes, any country which you say it has to be developed has a huge amount of energy generation and energy utilization capacity. Suppose you have a higher energy generation capacity and you don't have a higher utilization capacity, it cannot be a developed country. If you compare India as well as Japan, Japan has around 44 nuclear thermal power plants. It's a very small island. In area, it is 1/10 of that of India, or maybe still less, because I'm very bad in geography and social. I'm not sure, but if you can just look at the maps and all and observe it, maybe 1/10 or 1/15 of the space that you have it in India. But if you observe their energy capacity, energy generation capacity, and utilization capacity, forget about generation. If you look at utilization, a family has a utilization capacity of 5 kilowatt per capita energy consumption of a family of a size equal to 4 has 5 kilowatt. In India, as on now, our connected load to the domestic household is 1 kilowatt, and nobody uses 1 kilowatt. We are at around 0.5 kilowatt per capita energy consumption. Now, why the per capita energy consumption is higher in Japan is only because of its developed index. It has a huge industrialization, and the growth of industrialization is discussed from standpoint of your energy development, energy generation, and energy utilization concepts. So if you want to go from underdeveloped countries, still we are in underdeveloped stage. If you want to go from underdeveloped to the developed stages, our annual production growth rate should increase. Thereby, we have a very shortage of our resource, and you cannot use whatever fossil fuel you have it for now, and then you can't just leave Earth like this and give a very bad scenario for the next coming generations to go for energy starving society. So we talk about future energy requirements. In future energy requirements, we talk about the theme of today's topic, and this is one particular state where you look from standpoint of your pollution. This is one major concern. If you look at growth, there is equally global depletion. You observe that there is real pollution that is affecting it, and this particular estimate tells you around base load electric generation 32% is the emissions, combined heat and electricity 5%, heat is 2%, other industry 9%, residential commercials 10%. Then long distance road transport 1, aviation 2%, shipping 3%, variable electricity 12%, cement 4%, iron and steel 5%. And there are many things where you cannot eliminate. And this monitor, anybody can see, browse it. Just world's air pollution real time air quality indexes. If you observe it, in India we have only one place which is alarming, that is Delhi. Our NCT Delhi is one particular point. This is one, where it is, very unhealthy. We don't have any hazardous situations. Whereas if you observe it somewhere in Middle East, where we have more amount of oil exploration, uh, high temperatures and all, you observe that, and Europe and most part of Europe is, hazardous and unhealthy. And if you observe, if you come towards east, now China has some areas of northern China is basically on this particular index. So whenever you are looking at an issue where you want more power generation, you want prospect of industry, you want industrial growth, you want more amount of energy per capita, energy consumptions, and then you want to protect world. That's difficult to balance. So comes the concept of carbon emissions. You want more power production and you want less carbon emissions. Talks into the theme of today's talk. It comes as integrated gasification combined cycle of vehicles. So the concern was carbon emissions. There are we want to get down carbon footprints. If you want to get down carbon footprints, world has come out with trading because complete world runs on trade. If you finally understand things, it is how much you give and how much I take is the complete essence of this living world. So if you look at this, we are trying to reduce the carbon emissions from standpoint of what do you say, carbon trading, where company A and B are there. Company A can emit at up to 20%. Company B can also emit up to 20%. But company A, which is in America, has more orders and it can emit. It will say that it will emit up to 30% emissions, whereas a subsidiary company in India, where it does not have proper orders on hand, will say that I will emit only 10%, so that 30 plus 10, 40%, which was earlier equal to 20 plus 20, carbon trading. So carbon trading has put one particular Lakshman Rekha or whatever you can call an earmark on industrial growth in most of the developing countries, which is really bad. Hence comes concept of reduced carbon emissions. In reduced carbon emissions, we will talk about zero carbon emissions and carbon neutral technologies. Attaining zero carbon emissions is next to impossible. That is for sure. I'm pretty sure that whatever this particular world, when you talk about fuels, conversions, power generation, and all, it's based on carbon, and you cannot completely see to it. You take carbon and then complete emit it in such a way that complete carbon is utilized. C by C ratio, carbon conversion ratio from solid carbon to the gaseous carbon is 100%. Is impossible. Hence comes a concept of carbon neutral technologies. Carbon neutral technologies is you if you look at biomass consists of cellulose, hemicellulose, and lignin. And apart from that, there are highly complex compounds. To be frank, if you look at any biomass residues, agricultural residues, wood, and other forms of biomass of grade one, because we have already again graded them. Grade one, grade two, as well as grade three. Grade one biomasses, if you observe it, this particular biomass grow by taking carbon dioxide from atmosphere and release oxygen. So what is happening if you plant a tree? This particular tree has removed carbon dioxide from the atmosphere, and then it starts growing. After it has grown to one particular yield, what we will do, we will cut this particular plant. We call it as energy plantation, which will not affect the security, energy, food security of living organisms. We have to be very careful. Like now, whatever biomass you grow it, energy plantation in Brazil is an excellent example for this. Or Varnama power plant, energy plantation is another excellent example. Wherein, what you do, you grow this particular plant, and this particular plant takes carbon dioxide, grows. So it has removed carbon dioxide from atmosphere. What we will do, we will cut it, gasify it. We will not go for direct combustion. Most of the plants in India are using it on steam turbine mode, but my concept is slightly more different. So what we will do is we will gasify it, use it in gas turbines or combined cycle power plants, emit carbon dioxide back. So whatever carbon dioxide we have taken from the atmosphere, for plant to grow, the same carbon dioxide, we are releasing it back into the atmosphere. So what we are doing is we are not spoiling the situation. Whatever it is spoiled is spoiled. And then this particular, because if you observe it, the power sector generation is around 37%. It is 37 to around 40%. And this is the biggest sector. And we have to be very careful with this particular sector. Very, you cannot go for, reduced emissions. It is not, because as on now, thermal power plants has an efficiency of around 28%. 28 to 30% is the thermal efficiency is. Though people say that it's around 35 and all, on an average, all in India, most of the thermal power plants operate at around 30 to 32. Combined cycles, 3 or 4% is a big cake to eat. So if you look at this particular scenario, we will look into the biomass and this carbon neutral technologies, which you say that you are not spoiling the environment anything more. Whatever it is spoiled is spoiled. And let us at least give whatever we have it in our hand, because we realize after so many days that this is the situation. So if you look at the fuels, the basic fuels of it, this is one wonderful carbon, hydrogen, and oxygen triangle, wherein you understand about your fuels. Because when you start about power plants, you talk about fuel. Fuel is basic thing, and any fuel is made up of carbon as well as hydrocarbon. And suppose you say that it is a solid fuels. The solid fuels are your biomass. Then you have peat, coal, then you have char, then you have a peat. And this particular biomass contains lignin, biomass, as well as cellulose. Now, as you move towards carbon, you have solid fuels. As you move towards hydrogen, you have your gaseous fuels. So you have your liquid fuels made here. Then you have ethene, and then ethylene, and then if this is methane, and then this is your hydrogen. Now, what I will do from hydrogen, I'll just drop the perpendicular bisector onto this line, which is joining carbon as well as oxygen. This is my monoxide, carbon monoxide, and this is carbon dioxide, and this particular point is water, steaming, H and O, H2O. More the hydrogen, it will be towards hydrogen. That is you talk about the basic proportionality theorems in your plane geometries. And this is your oxygen. Now, please try to understand this particular solid fuels, if they are subjected to gasification. Gasification is anaerobic burning. We are not burning in complete air. Oxygen is starved. That means it is not stoichiometric. It is substoichiometric reactions, wherein you will try to convert solid fuels into gaseous fuels. This is what gasification deals. Wherein this particular fuel, on gasification of the solid fuels, have or constitute carbon monoxide, hydrogen, a part of steam, carbon dioxide, as well as methane, CH4. Methane is there because there is a Baudouin reaction as well as methanation reactions, water shift reactions. It is all thermochemistry, which will try to see to it the solid fuels are converted into gaseous. So suppose you have not gone with stoichiometry, you have gone with stoichiometry, or you've gone with XSR. That is what we generally do it in combustion process, wherein you get products of carbon dioxide as well as your steam. So this is where you talk about your combustion products. This is where you talk about your gasification fuels and all. So if you look at the gasification process, so suppose I have the biomass here. This is the biomass, and this particular biomass if I try to go in the absence of oxygen, that means I'm not going for heating in the presence of oxygen. There's a process of heating it in the absence of oxygen. This is your pyrolysis. Now this is have taken the world. People are working totally on this particular area wherein you are trying to look at how pyrolysis are working. This is pyrolysis. Then this is your hydrogen process where it will lead to complete hydrogen. Gasification agents, if you give air, it will move towards the gaseous fuels, and there is a process of steam process. So gasification process looks at conversion of solid biomass into gaseous products. We are just passing away that particular phase of liquids. If you have observed the very recent Government of India's bulletin on the scientific developments and the Prime Minister's message to the scientific community is to take up the problem of coal gasification. Thus, energies, our countries or any nation building policy of moving forward on industrial growth or taking up higher digits of your economy deals on energy protection, and people should have thought of that. There is definitely a scarcity of energy. Hence, they were looking at coal gasifications because we have a huge resource of coal. Whereas even biomass can also be taken as the secondary concepts of building up energy requirements. So if you look at gasification, my main concern is wood, because we have three types of biomass, as I was telling you earlier: grade 1, grade 2, grade 3. Grade 1 is a solid biomass, wherein you have larger proportion of carbon conversion ratio, C by C ratio uh, to ash. It is wood. Then you have liquid biomass, wherein the ash content is less, carbon residues are very less. And the third grade biomass is you will not get any amount of ash. What we are working with as of now, it is algae, which we are trying to come out from biochemical process. So getting grade 3 biomass in a liquid form from algae is still in the phase of research. And here, if you take wood, say suppose I take wood, go for drying and pyrolysis. This is thermogravimetric, cracking, and then you observe that large amount of mass is reduced here. This is clearly endothermic. It takes heat. Then this pyrolysis, gas and char, is subjected to partial oxidations, because we are not going for stoichiometric or what do you say, XSAF. We are going with substoichiometric reactions. Hence, oxidation is not complete oxidations. And we are very clear, like whenever we go for partial oxidations, it is monoxide formations are there, and the monoxide is required gas because it has a higher calorific value. Carbon monoxide as well as hydrogen constitutes your producer gas or water gas, what people say. And most of the European terminology and American terminology says like it is what do you say, syngas, synthetic gas, and odd, but we say it as a producer gas. Then this unconditioned producer gas is sent into a simple gas conditioning situation, wherein you give air here. This air, partial oxidation, unconditioned products, simple gas conditioning, and this conditioned air comes out. So if you look at a schematic sketch, this is one schematic sketch I just made it for the presentations. Biomass downdraft gasifier and cleanup systems. So suppose you have a draft, you have a gasifier. In fact, this particular study should be commended for one particular person by name Mukunda and Basappa from IISc Bangalore. They have a CGPL lab, combustion gasification professional labs at IISc Bangalore. They did good amount of work, and then with the motivational works of Dr. D.N. Reddy at the Center for Energy Technology of Usmania University, presently led by Dr. Narsimlu Sanke, the director of CET. We did work on biomass gasifications with the cleanup systems, wherein you have a downdraft gasifier. where the density of the biomass is higher, you will go for downdraft. That is one very simplistic way of putting it. Or in other way, if you want to reduce the tar content in the gas, you should not see to it that gas passes through the pyrolysis zone, or where thermal cracking has occurred, where there is more amount of tar. So in updraft gasifiers, you observe that whatever the gas which is moving from the top, will associate with more amount of tar. Hence, what you will do is a moving bed wherein the wood from the top will come down to the reactor. This is where you have drying zone, you have a pyrolysis, then you have an oxidation zone, then you have a reduction zone, wherein different reactions occur. At the reduction zone, the temperatures suddenly fall down because it is endothermic, and then you observe that carbon monoxide and hydrogen are associated with the gas along with carbon dioxide, because we say partial oxidation, but there can be reoxidation of this partial oxidation, and carbon dioxide can be formed, and then it passes into a gas cooler, wherein this particular gas is cooled, and because of cooling, the particles, the particle density would increase, and any physical association of the particles that is associated with this producer gas will come down into the bed, and then again this particular gas is passed through a scrubber, a centrifugal scrubbers, wherein this particular gas is centrifuged at very high speeds, as high as 1800 rpm in odd, on a three-stage centrifugal series connected stage of scrubber. The name itself is saying it will scrub, it will remove all the tar associated contaminants, physical contaminants, because we are not going for any amount of chemical treatment. They have ammonia, they have hydrogen sulfide, they have highly poisonous alkaline contents whose atomic number is more than that of benzene. Still, when we are looking at it, there is a possibility of going with chemical screening also. But as on now, our attempts, we went with physical screening of it, then took it to a cyclone separator, wherein if any amount of high density particles are still associated, they are centrifuged, they are churned, they are removed like as you remove your what do you say, cheese from the milk. You centrifuge it and remove, and then this particular gas is passed into the condenser as well as a filter, that any amount of moisture that is still present uh, with the producer gas has to be removed, and then this clean particular gas is passed into the combustion chambers. So if you look at it, this is the gasifier, because it is not to a small scale. Honest, to be honest, and I swear, this particular gasifier is only for 32 kilowatt electric capacity, wherein it will take 100 kilowatt thermal, heat capacities, and this particular size is huge. I'm just talking about, it is around 6 to 8 meters in height and odd, wherein this is your gasifier with complete SCADA. This is available at University College of Engineering, Usmani University, at Center for Energy Technology, Usmani University. Then you have your cyclone separators, then you have your filter and condensers. These are your centrifugal scrubbers, and this is your gas cooler, and this is your lockout for removing the ash as well as the ash pit. And mind you, this particular size is only for 32 kilowatt electric generation for coupling it to a gas turbine, which we have it at Usmani University. This is auxiliary airborne power unit of Vulcan engine. It is basically a small scale gas turbine is available, but but when you look at 100, 200 megawatt thermal power plants to be running on gasification cycles, just think how big this particular gasified size should be. And this is the biggest challenge. This is one particular challenge where people are facing as on today. The world is facing this particular problem in designing gasifiers, which should give uninterrupted power, uninterrupted gas supply to the gas chambers for burning, and to get power facility for large scale power plants. So The theme is now I want to integrate this particular gasifier to a combined cycle. Combined cycle talks about, if you have a gas turbine power plants operate at an turbine exit temperature of 540 degrees centigrade minimum. Whatever fuel you take it, the minimum temperature, if the plant is operating at its optimum efficiency of around 40%, gas turbine power plants have a higher thermal efficiency. Their SFC is low, BSFC, great specific fuel consumption is low. That's why power generation and instantaneous power production are all percent everything is good, but except one particular point is the turbine exit temperature is very high. It is around 540 degrees centigrade or around 700, 770 Kelvin and more, maybe around 800 Kelvin. It's higher. And this particular temperature going into atmosphere is waste. So what you do, you will try to recover, go for a waste heat recovery boilers, and then try to catch this particular heat, and then go for subsidiary steam generation plants. And from the steam generation plant, we subsidiarily run steam turbines. And this is what generally every combined cycle power plant does. So you call this as, combined cycles where you have only two generations, you have power. But now I have the future energy requirements where you look from standpoint of solid oxide fuel cells, because everybody talks about solid oxide fuel cells, or you talk about fuel cells, and you say that fuel cells will be replacing the energy requirements, whatever the very big power plants you have it in the next coming world. I'm not sure whether they completely replace it, but they will get part of it. Now, where you will get power as in CHP plants, combined heat and power plants, wherein you will also look at trigeneration. This is the picking topic. This is one topic where enormous amount of research funding has been there from Europe. Netherlands. Netherlands is neither land nor sea. As you know, it is 1 inch below sea level. They're concerned with global warming. They have poured millions and millions of euros into the market to see to it, you reduce your emissions down. And trigeneration is one particular concept. Where this is your gas turbine compressor. The compressed, no, this is the gas which you are, I'm sorry, this is the gas which you are getting it from the earlier biomass cycle, gasification cycle. Then you go for a boost compressor. So you have to give power here. And then this boosted producer gas goes into solid oxide fuel cells, wherein this solid oxide fuel cell produces power. Then these SOFC gases will go into the burner of the gas turbine and then burn, produce power here, and the exhaust of the gas turbine is again goes into the waste heat recovery or exhaust for the steam bottling cycle and produce heat and power. So you have CHP, combined heat as well as power. So if you look at one particular point which I want to tell is, I'm not really others talk on fuel cells or, but I have used SOS, solid oxide fuel cells, apart from proton membrane fuel cells. I just took it, into my analysis of, integration plans, wherein, SOFC, solid oxide fuel cells, this solid oxide is only because of this, conduction medium, whatever the medium that I have it here, this particular medium is, is a solid medium and highly thermally conductive. And I have an anode and I have a cathode. My electrochemistry clearly says that there is movement of electrons from cathode to anode, negatively charged to the positively charged. And in doing so, this particular electrolyte, where it is used as a conduction medium, which is erythria doubly sterilized zirconium electrolyte, should be at a very high temperature and it should be highly thermally conductive. Here, the studies have been made here about thermal diffusivity of this particular electrons from the cathode to the anode. Now, this is where you are getting your electrical power. Now, where does this electrochemistry of solid oxide fuel cell fit into my gasification? Now, if you observe it on anode side, because cathode as well as anode are submerged in different environments. One environment is your fuel environment, other environment is air environment. The fuel is monoxide as well as hydrogen. And where do I get it? I get it from my gasification. From here, I will try to get. I'll put wood, I'll get monoxide as well as hydrogen. And this monoxide and hydrogen, when it is fed into the fuel cell, not into the huge quantities as you feed it into the gas turbine combustors and all, rather in a partial and required capacity as that of your fuel cells, you observe that this carbon monoxide, it adds up, two ions of oxygen, forms dioxide, and two electrons are released. Similarly, hydrogen, it adds up, two oxygen ions, forms water. This is what yesterday one of the speakers was saying. I think it should be, yeah, it is Aditya. Dr. Aditya was telling yesterday, formation of water is not a single step chemistry. Yeah, it is not infinite fast chemistry. It is finite rate chemistry wherein you have reaction mechanisms, and in doing so, you have electrons, and these four electrons, a half molecule of oxygen or one molecule of oxygen will take four electrons, or half molecule of oxygen takes two electrons and releases this oxygen ions. And in doing so, you are having a current. You are having a current. This is your solid oxide fuel. Very good. Wonderfully understood about electrochemistry of SOFC cell, unless and until you don't get the fuel. So we have to be those who are in fuels, combustions, thermal engineering analysis, power plants, and all. Of whatsoever chemical analysis cell people develop for future energy requirements. Now we should not get away from this fuel aspects, because anode material engineers are working from standpoint of your anode material as well as cathode materials as well as electrolytes, and we have to look into the standpoint of fuel requirements, gaseous fuel requirements, wherein we will give it some standpoint of your gasification. So there are issues. Issues is maintaining temperature of solid oxide fuel cell at about 1000 degrees centigrade. So maintaining it is, you have to maintain it with isothermal conditions. Electrolyte should be oxygen ion conduction mediums. That's why we are going for Eritrea doubly stabilized zirconiums. Wherein this is what I was been doing it from last 2 days, sitting and then drawing out your IBGFC modules. Now, this is where I start, and I take wood and then dry the wood, and because wood has moisture, and the moisture will affect the gasification. We have observed that lower the moisture content, higher is the composition of monoxide as well as hydrogen, lower is methane. And when you try to increase the moisture content, because moisture content varies from around 10 to 30%, and higher the moisture contents, we are observing that methane is increasing, but monoxide is reducing. There are various effects. So this particular wood is sent into the gasifier, and from the gasifier, this particular wood is gasified, because this is not a small thing, because this is only a small rectangle, but this particular process is very cumbersome. Now, wood has to be dried, then it has to be pyrolyzed, pyrolysis, then you observe it partial oxidations, then you have reduction, and then you get a P-gas, producer gas. And this particular producer gas is passed through a heat exchanger, wherein your earlier whatever air you are sending into the gasifier has to be reheated back. So whatever is the producer gas that is coming out of the gasifier reactor, is going at a higher temperature. So I am recovering heat by sending air and then again passing back into the gasifier, thereby getting into thermal efficiencies. And then it is passed into a cooler, wherein I spray water and then cool down the gas. It is basically a process in which liquid gas interaction heat transfer, direct contact heat transfer setup. And then this particular gas is again sent into the scrubber. From the scrubber, it is being cleaned process, because the issue is, because IISc Bangalore has done excellent work on, especially G. Sridhar, Mukunda, PJ Paul. Professor PJ Paul's work has to be definitely appreciated from standpoint of IC engines, wherein they have expanded this producer gas in IC engines produced power, and even they have commercialized the technology. But one biggest feedback from the market was the engines were getting clogged. The valves are getting clogged. The valve timing is changing. Many of them quote that it is because of, manifolds. There is clog due to which there is severe pressure drops and all. All that is only because of tar associated with this particular gas, and this particular gas has to be cleaned. So all this, effort is being done to clean the gas, passing through the cyclone separator, then through the filter, then through the boost compressor. It is sent one particular part into the fuel cell, monoxide as well as hydrogen, wherein you are getting electricity here. This is first generation. This we call it as first. Then this particular gas is sent, it is bypassed, it is sent back into the gas turbine combustion chamber, wherein it is directly burned. This is not what the people as of now doing. Most of small power plants, like, I don't want to pick names, 6 megawatts, 2 megawatt biomass power plants, 11 megawatt thermal power plants, say that they are on biomass in and around Hyderabad, in Telangana specifically. They generally are using this particular wood. They are heating it directly, incinerating, they're heating it, and this particular heat, they're giving it to water, and that water, they're taking out steam and burning it in steam cycles. And still they quote it as biomass power plants. But as far as my understanding goes, biomass-based power plants and integrated gasification technologies should talk from standpoint of pure, gas turbines. Vernamo, I quote Vernamo power plant, which is in Sweden, to be state-of-art power plant, wherein it was operating 150 megawatt capacity on, integrated gasification combined cycle analysis, wherein you burn your producer gas here, and then those products of combustion are expanded in the turbine. You are getting second generation power, first generation power, second generation. And this particular, as I was telling, this particular exhaust is at a higher temperature, around 540 degrees centigrade in a centigrade scale, or in Kelvin add up 373. This particular gas is again passed into a WRH, waste heat recovery boilers. Or yes, you can just pass it. Initially, this is a regenerator, which you call it in your gas turbine cycle, because gas turbine has a compressor, combustion chamber, turbine. So what we will do is, whatever the air we are taking from the air handling unit, this is outside air, and which is split, one phase going into the gas car, other phase going into the compressor. From the compressor, when you are passing it into the combustion chamber for combustion process, because it passes all through this fuel cell and then comes back into this combustion chamber. When it is doing in so, what we are doing is, we are reheating this reheating parts of air. Thereby, you're trying to improve the thermal efficiency of gas turbines. What we learn in basics, like reheating, regeneration, and intercooling, increases the thermal efficiency of the combined cycles. We are going for regenerations here, and this particular exhaust, which is in blue color, it comes into this particular waste heat recovery boiler, WRHE, wherein you put water from outside, and then water becomes steam at its saturation temperature. Here you expand it into the steam turbine. You are getting a third generation power, and from steam condensate, either you cool it down, or you try to see to it, you go with this is the pond. Again, you recirculate water back. So we were talking about first generation, second generation, third generation power generations. They're really good to look from standpoint of power generations, but so many issues are there. This looks like a schematic thing wherein I have drawn the pressure, temperature, as well as mass flow indexes and all. But in actual practice, we come across various problems. This is this is, say, I am sending this producer gas into the gas turbine combustion chamber. And then how this combustion is occurring, because combustion should be looked from standpoint of stability and instability. It adiabatic flame temperatures. It's hydrogen ion propagations, hydroxyl ion propagations. What is its ignition? Where does it catch? How much amount of time does it catch? And on. So these studies were being discussed here. This was our earlier observation at Center for Energy Technology, wherein we did some experimental analysis. I think one of my colleague, Ravi Kumar, would be there. He would be appreciating the work along with Ravi Kumar. I was been doing it. This is one where we have designed one very big barrel, if you say, or I can say a combustion chamber. We designed a combustion chamber, and wherein we have mixed this fuel as well as air in a substoichiometric conditions at its stoichiometric conditions, and we have used it in the combustion mode. And these are the flame structures what we have been having. This is at air fuel ratio of 1.1. Producer gas, beauty of producer gases, its air fuel ratio is 1:1. And this is at slightly rich air. So it is around 1.25 odd. And we made some CFD analysis on the combustion. And then we were looking at how the flame structure was moving. This was talking about it from temperature of exit. We are getting around 796 Kelvin turbine inlet temperatures, very cool turbine inlet temperatures we've been used. So when you look at this particular issue, the biggest issue is gas turbine combustion chamber. So if you look at it, any gas turbine combustion chamber should have easy initial ignition. It should have a stable operation over range of conditions. Then it should have a complete combustion with minimum pollutants, sufficient mixing to achieve uniform exit temperature, low pressure, high efficiency, minimum size, weight, and cost. It's something like getting a married nowadays for young boys. This is how things go. The combustion chamber requirements are very huge, and the size is very less. It's not even 6 to 8 inches long. If you're looking, I'm not talking about the test facility what we made it, but in actual practice, when you look into the gas turbine on a cannular, gas turbines, you have around 24 cans placed around the circumference of your gas turbine. You observe the size is very less, and the power requirement is more. So the basic things are, these are the points that have to be looked. And if you want further information regarding the combustion characteristics and how we made it, you can refer to this paper, which is in ASME Congress. And issues associated with biomass integrated gasification, gas turbine technology. So first, we are trying to look at gas, biomass integrated gasification with gas turbine technologies, because solid oxide fuel cell is again a bigger issue. So first, let us look at how we will integrate biomass to your gas turbines. Combustion stability is the biggest problem when gas turbine is running with LCV gas, because natural gas has a calorific value of around 24 to 28 megajoule per mm cube. And if you are looking at liquid fuels, something like your natural your kerosene, ATF, aviation turbine fuel, they have around 36 to 38 or even 40 megajoule per nm cube is the calorific value. Whereas calorific value of biomass derived producer gas is 5 to 6. Believe me, it is 5 to 6. People say 8, but it is shunting, or it is hunting from 5 to around 8 megajoule per nm cube. and drastically your power input to the combustion chamber has reduced. And how we will correlate is energy density is one particular parameter which will help. Because for methane, it is 16 is to 1 is the air fuel ratio, 16 parts of air, 1 part of fuel. Whereas here, 1 is to 1. So if you take 1 cubic meter, or if you take 17 parts of a mixture, you have 1 part of fuel, 16 parts of air in case of methane, whereas in case of producer gas, 8.5 parts of fuel and 8.5 parts of air. So you are injecting more amount of fuel in the given volume with a lower calorific value, thereby you are trying to compensate the energy scarcities. So combustion stability is the biggest problem. This is where we did some off-the-design performance analysis also. And then increasing pressure loss in combustion chamber due to high admitted volumes of low calorific values. Then combustion chamber of gas turbine should be replaced when operated on lower calorific value fuels, which increase the cost of installation by about 20% of high capital cost. So this is one issue. And then due to presence of higher volume percentage of hydrogen in producer gas, combustion sustainability is attained, which may contradict statement one, but leads to backstream propagation of flame in ultra low NOx combustors, NOx combustors. So if ultra low NOx combustors are not used, then pollutants is the biggest concern. So it is something like James Hadley chase. I run behind you, you run behind me. This is what it is. Then hardware modifications is to be made for existing gas turbines working on natural gas, which OEMs will never do it. So we have to do the modifications, or you have to go with blending of the fuels. So possible solutions to identified issues are designing ultra low NOx combustion chamber to meet the 25 parts per million of NOx regulation on liquid fuels, and for less than 10 parts per million on natural gas. Co-firing of natural gas with producer gas in the proportion of 50 is to 50, we call it as B50 blend, such that hardware modifications need not be addressed. So this is where many of the research works are going on, and we have to look at natural gas as well as producer gas chemical combustion characteristics, which is my next part of study. So cogeneration of biomass integrated gasification gas turbines with steam bottoming cycle and integration of solid oxide fuel cell is your state of art as on now. So when I'm trying to blend natural gas, with producer gas, I should look at adiabatic flame temperatures. You observe. Yesterday I was asking Aditya about Cantera and mechanism files. We were been using Cantera code. Cantera is an excellent open source code available for chemical combustion characteristics. Those who are interested to work on chemical combustion characteristics can look at Cantera, Cantera, Cantera code, wherein you have different mechanism files. We took GRM file, Gas Research Institute mechanism files, wherein this is equivalence ratio. Most of you know it. Equivalence ratio is ratio of fuel air ratio, actual to fuel air ratio, stoichiometrics, and if it is one, you call it as stoichiometric. If it is less than one rich, greater than one lean. So you try to look at situations wherein adiabatic flame temperature is at an equivalence ratio of 1.1 has reached a maximum of 2350 Kelvin odd. And then what we did is you cannot just take one particular fuel, test its combustion characteristics, and then say this is done. Because our replacement is methane air. Hydrogen, many of them started working on hydrogen, but hydrogen has the highest calorific value, 144 megajoule per nm cube. And as highest calorific value, it has highest risk also. It has a very low diffusion coefficient, or in other words, highly diffusive fuel. So the time you look, because whatever the time you are looking at here is all microscale time, and within 2 into 10 power minus 3 seconds, complete combustion is over, and then you have to pull back all the particular heat. So hydrogen air combustion is basically the biggest challenge for people working on combustion chambers. But to have a, what do you say, a reference, I was using hydrogen air, then producer gas and methane air. This is where I was having hydrogen air fuel, yes, this blue one. Then producer gas is this particular orange line, and then this is your methane air flames. And we could clearly observe that corresponding to an equivalence ratio of 1, producer gas is matching. It's matching for most of the chemical characteristics of hydrogen as well as methane. That means adiabatic flame temperatures are higher. That means whatever combustion chambers we have designed for methane, we can successfully use them. The material restrictions would not be a bigger issue for producer gas. This particular analysis will tell that should I change material of the combustion chamber if I'm going for producer gas or not? Need not. Because adiabatic flame temperatures are in the same range. I hope combustion chambers might have been designed for a factor of safety on thermal shocks and odd for values of around 3 and odd. Now, this particular producer gas has almost met the requirements. And if you observe it, ignition time with residence times, estimation of ignition time, and producer gas has taken around zero point 0.4 0.4 into 10 power minus 3 second ignition has started. It has within a fraction of second, the temperature has raised from around 1000 Kelvin because already we have compressed it. Whatever gas you are getting it from the gas fire is around 150 degrees centigrade, then compressed 400 degrees centigrade, around 673 Kelvin, and then reheated, passed through your SOFC, solid oxide fuel cells, in some amount of heat that it would have taken, would not have pre-ignited, then immediately this has ignited, and then you are observing that its ignition temperature, it has reached a temperature of 2552 Kelvin, and this is your ignition. So estimation of ignition time with residence times, and whenever you are trying to look at the combustion, one particular ion you have to be very careful. One particular thing that we have to be very careful. This is clearly your estimation of hydroxyl ion, OH ion mass fraction in producer gas air mixtures. So if you observe it, hydroxyl ion propagation will tell about complete burning of public fuel. If you are looking at hydroxyl ion propagation, that will clearly tell you whether your combustion is complete or partials. So yeah, this is hydroxyl ion, and then estimation of ignition temperature at gas turbine conditions, because gas turbines operate at a higher pressure. So ignition limits are obtained at around 839 Kelvin. And then this is prediction of combustion characteristics of producer gas at 4 bar with hydroxyl ion mass fraction propagations. Hydrogen ion mass fractions. Just a minute, 1 minute. Can you, hello? Can you see the screen? Hello?
No, sir.
Can you see now?
Yes, sir. Yes, sir. Now it is coming, sir.
Yeah. So, Can you see the presentation?
Sir,
Hello?
sir.
Yeah.
Yes, sir, we can. Please proceed.
Yeah. So, what our work was like, we did some CFD analysis, wherein we have plotted how temperature was varying and how pressure variations are occurring, how kinetic energy is getting dissipated, because we have used non-premixed combustion, non-premixed spray combustion, droplet combustions with thermal analysis. And then I was also using some amount of what do you say, uh, uh, kinetic energy dissipations in the combustion chamber. And then we are discussing how pressures are varying it and how we have dilution effects. And this is where we are getting turbines. And whenever you are designing combustion chambers, we have to design it for more amount of turbulence. And this is one particular study what we made, wherein the combustion chamber is being fired with one is methane and other one is with producer gas. And at methane, the temperature at the turbine inlet temperatures are slightly lower than compared to the turbine inlet temperature corresponding to producer gas. This is a risk because TIT, turbine inlet temperature, or what you call it as T3, or temperature entering into your combustion chamber, should always be less than 1600 Kelvin. But another issue that comes out is if the temperatures are higher than 1600 Kelvin, you are observing that nitrogen that is being sent along with the air for combustion is chemically active. It is not inert. It is chemically reactive, and then this chemically reactive nitrogen with oxygen forms pollutants. Hence, the biggest problem that we will encounter if we are going with the same combustion chamber of firing the producer gas is higher turbine inlet temperatures, which will also burn the parts of your gas turbine. And how to protect them? Just now, Vamsi was telling, you go with thermal coating and then thermal spray coatings, and then protect this particular product from your what do you say high temperature issues. But rather than protecting materials, what we have to do is we have to quench, and that is where the biggest question comes. How much amount of secondary air, how much amount of tertiary air should be sent into the gas turbine combustion chamber? I'm telling you, still Pratt and Whitney is still doing empirical values. They are still doing only based on some compounds and all. There is no specific scientific method exactly established in gas turbine combustion chamber design, wherein that you have to give clearly that 20% primary air, 30% secondary air, 35% tertiary air, dilution air is another 5% at all. No such metrics exist till now. And still we are hunting. Still we are hunting, to establish, scientific procedures to maintain, constant, stabilized, distributed air flows within the combustion chamber to get, around 1200 to 1400 turbine inlet temperatures, wherein you get, better, better mixing of the fuels and all. And what I did is, after doing all this, showing all wonderful colored diagrams, line diagrams, and all, would definitely not suffice. The work we started, working out how things are changing. What we have given initially in dryer, we have given wood, how much amount of mass flow, and then finally we calculated everything. One compound is 1 kg of wood. We give you 2.5 nm cube of gas. Suppose you are burning 1 ton of wood, or sorry, if you are gasifying 1 ton of wood, 2.5 tons equivalent of gas is obtained. That's a wonderful phenomenon wherein you can go with mass production of power, but there are few issues associated with it. One is gasifier, and second one is gas turbine combustion chamber, and all other things are systematically they are standardized. Gas turbine combustion chamber has to be modified for your biomass based producer gases. And then waste heat recovery boilers, they only take heat and then it's the steam bottling cycles. And solid oxide fuel cells has to be integrated into this particular cycle to attain higher efficiency. Then comes your energy balances. We made energy balances. What we did earlier is we made what is mass flow, what is the pressure, temperature that we are maintaining. Next is we are looking at energy balances, how energy is balancing. Actually, we made exergy analysis also. Rather than energy, exergy is always, suggested because, exergy calculations tell where it is getting destructed. Wherever you have exergy destruction, there you have to go for minimization of your exergy destruction because you cannot stop exergy destruction. That is unavailable energies. So what we did is initially I am just presenting out the energy analysis. We also did exergy analysis of 12 megawatt biomass power plants. It was published. It's available. So we have attained three generation power. One is from solid oxide fuel cells, other is from gas turbines, other is from steam turbines. And it, like compressor takes in work. And our analysis, this is one particular work I did it for a thermal power plant where it is still under NDA, non-disclosure agreement. So I cannot give out what quantity of wood or odd we have been giving out, but I can give out the final output of power, which will not affect them at any point. It's around, almost 200 kilowatt, 0.2 megawatt is the output of the pilot scale what we have designed for this gas turbines. And then recovery is at around 25 kilowatts, around 30.8 kilowatt is the steam turbine output. Then we have a solid oxide fuel cell, which is having around 22.34 kilowatt. So this is your tri-generation plant, wherein the advantage is this is base load operation. Steam turbine is always a base load operation, because gas turbine is always a peak load operation. So we have synchronized a peak load with a base load operation with power requirements to utilities by SOXs. The issues associated with integration of SOXC, when you look at issues associated with integration, thermal insulation of fuel cell to maintain isothermal condition. Thermal insulation is the biggest problem. We were saying that we were clearly saying that solid oxide fuel cells have to maintain a temperature of around 1000 degrees centigrade. Eritrea doubly stabilized zirconium conduction membrane should have around 1000 degrees centigrade. That's a temperature, and I have to maintain it at that highest temperature. Please refer to the best of the best literature that is given in SOFCs, and people are struggling hard to maintain this temperature, and it is we the thermal engineers that come down and then present a solution for thermal insulation. And because it's a chemical cell, and you cannot just thermally insulate it by any way. And those who are planning to take up any further research, those who are looking for excellent research topics to be written for government of India to get funding and all, this is one area where you can really do it, because our perception of view is down the line 30 years, we have to integrate our researches. And then thermal insulation is the biggest problem. Then comes steam and gas turbine cycles. You have a steam cycle, you have a gas turbine cycle, and both of them has to be pinched. You have to pinch it at one particular point, arriving at pinch point between steam and gas turbine cycles. Because it is so easy, like I'll say the exhaust coming from the gas turbine and will enter into the steam turbine, but the operating pressure of the steam turbine and the exhaust pressure of your gas turbine should always mix. And if there is any slight variation in the load, you observe that there is slight fluctuation. So that means if they are running on design point, it's okay. But if one particular component moves from design point to off design, the other particular component starts fluctuating. This you call it as asynchronous, not synchronous, but asynchronous operation. So Another research problem which I want present it to you that arriving at pinch points between steam and gas turbine cycles. And it is not easy. Many of them are paid huge only for assessing this particular pinch point between steam and gas turbine. Then the third one is solid oxide fuel cells. Whatever you are using it, these electrodes, you have a cathode and anode, you have a metal surface oxide reactions. At metallic surfaces, you have oxidation reactions, and this particular oxidation reaction is the biggest problem, and consumption of electrode is another biggest one. That means consumption of electrode. This is your Faraday's law, where of electrolysis. It talks about that the electrode, there's a consumption of the electrode because of metal oxide surface reaction. And this should be looked from standpoint of electrochemistry, and wonderful problem for people working on thermochemistry. Then operating pressure of fuel cell to overcome the choked flow conditions. There's a situation where the fuel that is passing through this particular fuel cell, should have a continuous flow. Choked flow need not talk just only about maximum mass flow rates, but also the surge or disturbance in the fluid flow over this fuel cell will cause a severe issue in operation of this particular fuel cell, wherein the rising temperature will increase. And you cannot maintain isothermal condition of the fuel cells. And this is where those who are planning to work from standpoint of your fluid flow analysis, subjected to thermal gradients, there you can definitely take out one particular analysis and then start working out the pressure balances pertaining to choked flow conditions. Then, above all, so I look at all these 4 points as one. The biggest point that always sits itself is gasification. Gasification itself is challenging, but still, we love to do so. So, the conclusions and future work are clean energy available through efforts. I was saying earlier, my presentation started basically with energy demand, fossil fuel depletions. Then we started about talking about carbon trading and all. But finally, when you are looking at it, we could really get clean energy available if there is solid oxide fuel cell integration. Pollutant levels decrease in IBG-XC models. Yes, there's a possibility of, definitely there's a possibility because, we are going on carbon neutral technologies. We are not going with, zero emissions. We can't claim it, but we say that it is, reduced. Exergy analysis will indicate the critical areas of exergy restriction, which have to be modified for better exergetic efficiency. So I recommend that whenever we are going for thermal power plant analysis, combined cycles, and then we are integrating with highly sophisticated, non-asynchronous, components such as steam turbines and gas turbines with SOFCs, exergy is must. Exergy analysis is must. So, and making an exergy analysis on a combustion chamber is really a challenge. And still, we try to go ahead with, rather than microscopic, we go to macroscopic. Then development of new materials for high temperature stable operation of solid oxide fuel cell is always advised. So I would like to acknowledge people, my professor, Dr. MVS Krishna, professor at CBIT Hyderabad, without whom I would have never taken up the gasification work, along with Dr. D.M. Reddy, professor and earlier vice chancellor of JNTU Hyderabad, retired professor from Usman University. Nevertheless, Dr. Narsimlu Sankhe, the present director at Center for Energy Technology, Usman University, who has helped me out all through giving all the facilities, or else I would have never seen such excellent technology and facilities that are available. So I really thank Dr. Narsimlu Sankhe and Dr. M.V.S. Krishna, and in absence, Dr. D.N. Reddy Garu, who has really carved most of it. So this is what I have it for today. Let me come back, stop sharing,
Thank you very much, Sharma sir.
Yeah, I would like to take some.
We enjoyed your session.
Thank you, sir.
Any
Dear
questions?
participants, if you have any questions, please post in the comment box. Sharma sir, there's a question from
Yeah.
Dr. N. Janardhan.
Yes. Dr. Janardhan, this particular gasifier, what we did it is a stationary bed gasifier. Fluidized bed gasifiers are state of art. Stage 2 and stage 3 we have it. But as of now, whatever gasifiers we have it, we have a stationary bed gasifier. But when you go back and look at power plants, you want fluidized beds with the stage 1, stage 2, as well as stage 3, wherein mass consumption is the biggest criteria. Because gas, as you're supplying gas, your fuel should also be consumed. Gasification time takes around 7 to 8 hours. So you cannot wait for the next amount of lot of fuel to come down. Hence,
Okay, sir.
yeah.
Sir, another question, please.
Does the type of wood matters in gasification? Yes, sir. Type of wood definitely matters in the process of gasification. Because if you are taking wood, basically a subabu, uh, the thing is, you should look at carbon to hydrogen ratio. In wood, whenever we are looking at carbon to hydrogen ratio lower, if you gasify it, you will be getting carbon to hydrogen ratio higher in gaseous fuels.
Okay, sir.
So we have to be very careful with this particular wood. Suppose if you are taking cotton shells, groundnut shells, if you are taking coconut shells, it is very difficult to gasify this shell. We have to be careful with shell because it is the structure of the wood is also mattering. Some
So
parts,
what is the methane percentage and the hydrogen percentage in the gas, sir? When you do volumetric analysis,
yeah,
so you will detect.
carbon monoxide is around 18 to 20%. Hydrogen is coming out between 16 to 22%. Methane is very less. It is 2.2%. Methane, it is even less than 1%, whatever we have observed in the gas chromatograph studies. And carbon dioxide is equivalently higher. Sir, there is one reaction known as water shift reaction. Whatever the water that is formed in the process of oxidation, it will shift back into hydrogen. So gasification agent is a major point. If your gasification agent is air, you are having lesser component of hydrogen. If your gasification agent is steam, you are having a higher component of methane as well as hydrogens. And there is activation of Baudouin reaction, wherein carbon dioxide will shift back to carbon monoxide. So if we control methanation reaction, water shift reaction, and Baudouin reaction, I think we can get an estimate of around 20% carbon monoxide, around 16 to 18% hydrogen, and then 10% carbon dioxide, then around 2% methane. Rest is methane. The rest is nitrogen. Sorry. Yeah. Thank you.
Thank you, sir. Thank you so much.
Sir, Sharma sir. Hello.
Yes, Ravi. Yes, Ravi.
Yes, sir. Now I would like to give Bhargav Chandra sir for proposing vote of thanks. It's over to Bhargav Chandra.
Yes.
Hello,
Yes, sir. Audible.
am I audible, sir?
Yes, sir.
Yes.
Yes, sir.
Thank you, sir. Dr. Srinivas Sharma, sir. We call him as Sharma, sir, with love. Is an inspiration for many teachers in our college, not only in our college, outside our college also. And let me tell you that there are no boundaries for his knowledge, and his understanding is not only limited to all branches of engineering, but it extends to mathematics, sciences, artificial intelligence, programming, CFD, numerical methods, spirituality, mythology, arts, as well as he's a good sportsman also. Okay. So he's a faculty with image. loved by all the students. So it's an honor to be his colleague. And he's one person who encouraged me about 6 years back to take up a subject, heat transfer, the subject which I dreaded most, actually. So I took up that subject and handled it for 3 consecutive years with his motivation. Thank you very much, sir, personally. And thank you, sir, for taking all the pain in conducting this particular webinar. And thank you, sir, for enlightening us with the wonderful lecture.
Thank you.
So we always look up for his presentations and lectures. Always we'll be waiting. We'll be like itching to listen to his presentations at the college. And whenever we pass by a classroom when his sir is taking some class, we just stand there and try to listen his lectures. So it's like inspiration for all of us.
Thank you.
And sir is a very nice person, very kind-hearted, very approachable. Anybody can approach him for any kind of help. Like I said, his knowledge is not limited to only mechanical engineering. His roots of knowledge are extended to all branches and sciences also. Not only that, sir always speaks about mythology, spirituality, a God-fearing man, I would like to say. Thank you very much, sir, for this wonderful presentation and enlightening us. Thank you very much. So I'll hand over to Kumar, sir.
Thank you.
Sir,
Ravi,
sir, yeah,
Madam is not available, both. So we'll start and complete the issues.
right, sir, fine, fine.
Respected dignitaries, uh, now I take the other role of being the convener. Uh, Today, our head of the department, Dr. M. Madhavi, as well as the principal, Dr. G. Kanthadurga Madam, both of them are not available. It is because of some very busy schedule what they have it for tomorrow's university requirements for a compliance and all. Just now I got a message while giving the lecture. I would again tell one more point. Like we missed one lecture from professor from IIT Bhubaneswar, Professor Seshidhar Kundaraju, because he had one immediate online meeting today, which he discussed to me early morning, or else it would have been a marathon session today. And I would present my convenience talk now. Totally 130 participants have attended this particular webinar, and this particular webinar was paid webinar, and I thank you very much for honoring this particular registration fee. We had one thing in our mind. That particular point, what we went through is those who are really interested in thermal sciences and fluid flows, let them join. It's not like, as there is a webinar, let them join. One more webinar, chalo, we'll join. Today, I've seen around 10 notifications of webinars have been published, free of cost. But whatever we have observed is, if there's a paid webinar, this particular thing will send very serious, intentions and motivations to everyone. There is one particular point which I want to say. And whatever registration fee that we have collected will go to the resource persons, except me. And all that will be sent in kind, like, one particular bag or any other, book or any honor from advances in thermal sciences and fluid flows. The first day session was given by Dr. B. Ganeshan, sir. Let me tell you, it just took me 1 year to get his mobile number, and he took only 1 minute to accept my invitation. That is the greatness of Dr. B. Ganeshan. The plenary lecture was excellent and wonderful, which I really loved it. After looking back his book again yesterday, I could find whatever he was talking, which I could not see the time when I was coming back and talking in the class. The second lecture was presented by Dr. P. Ushasri Madam. Dr. P. Ushasri Madam has given an excellent overview of some CFD analysis. Madam presently guides around 12 students at University College of Engineering, some university in CFD thermal turbo machines. And honestly speaking, I'm also a student of mine. And and the third lecture was K. Aditya, Dr. K. Aditya from Frame Lab IISc Bangalore. Aditya has earned a lot of respect and awards uh, uh, in his career starting way back from 2007. And his lecture on combustion dynamics, combustion stability, combustion diagnostics. In fact, he was talking about combustion diagnostics, which people will always look. People like S.R. Kearns or Kenneth Ku or people like Chandramohan and Sharma from IIT Delhi. They just look back when you talk about combustion dynamics. It was a wonderful lecture from Aditya. And whatever works he has presented from the plain lab are highly appreciated. Then the fourth lecture was, an excellent lecture from our Professor V. Umameshwar, who is also vice president of Hyderabad SAE chapter. Actually, we want to launch this from SAE Hyderabad, and at the last minute we went back and we launched it to SAE MVSR Collegiate Club. And the lecture was completely on mathematical fundamentals and fluid dynamics. I'm telling you, it would have taken professor maybe at least 40 to 50 hours to type down all those equations. Yesterday, sir has sent me a few notes, and then when looking at it, they were all completely typed by professor. He has not taken it from anywhere, no images, nothing. Mostly he has been, typing it, and he's an authoritative person in mathematical modeling of fluid flows. Uh, and those who use the CFD software and those who plan to build those algorithms, all those require that mathematical fundamentals, which is really a very difficult task, Herculean task for a mechanical engineer to come down and talk about vector calculus and principles on finite volume methods and finite volume methods applied for fluids. Then we had today's morning session by Dr. M.V. and Vamsi. Dr. M.V. and Vamsi, for the last 4 years, he he was earning award by award. Every year he is earning award by award. So most of his work is related to thermal spray and powder metallurgy aspects of it. He he is presently working now for Pratt and Whitney because he has an Indian non-disclosure agreements, and he was instrumental in inspecting the severe crash of two particular Malaysian airlines and other particular airlines in the process of its flight. And he is also one particular person who is instrumental in post-investigating the gas turbine combustion chamber for sudden crash. And the lecture of Emilian Ramsey was damn good. So, and I just took this particular stage to replace Seshidhar Kondaraju, who was not available for today's lecture. This and Department of Mechanical Engineering. Now I'll take the next role and then talk on the behalf of Head of the Department Mechanical Engineering, Dr. N. Madhavi. Madam has personally requested me to add these few words to the perusal of the peers and distinguished participants of today's valedictory function. Uh, in words of Madam, I am presenting about the Department of Mechanical Engineering has was started in the back 1981 from the inception, 39 long years of history. We have highly qualified faculty, 36 in number. We have 4 professors, 6 associate professors, and very enthusiastic assistant professors. We have Osman University recognized research center, MVSR Engineering College, and we have SAE activities. And very recently, yesterday information, I would like to congratulate our one of our professors, Dr. J. Kandaswamy Garu, who has got a RPS project from AICT. And then the Department of Mechanical Engineering is very strong in thermal production, design, as well as industrial engineering. And all particular streams are viewed as the eyes of the college. And the Department of Mechanical Engineering has contributed a lot. And we always believe that students are highest strength. Our strength, sir, actually today, whatever speakers we have three particular resource persons as our alumni. We have another two alumni who have been working for Argonne National Labs, Subhendu Soam, Dr. Subhendu Soam, and then we have Anshul Kaushik who was working for GE, then went back to Samsung. Uh, we tried for them. In fact, it was last minute we could not get. Our strength is our alumni, our projects, and then our faculty. And with this, I would request our my colleague Ravi Kumar sir to present. And last one point I just want to say, certificates will be provided to you. Certificates will be provided to you within 3 to 4 days. Please give us some amount of time. We will give you a wonderful commended certificate because we want to look who are actually registered for the thing, and then we will give them through the mail, M. Ravi Kumar. And one particular point I want to add up, M. Ravi Kumar, who is there on the screen, he has done all the things. He is behind the complete running of this particular webinar. Ravi Kumar, bottom of my heart, I thank you very much for whatever work you have been doing. He was maintaining two particular, computers, one for admit, one for logging on, and other is streaming directly into YouTube. First time he had streamed directly into the YouTube. So I would request Ravi Kumar to present your over.
Thank you, sir. I'm audible, sir.
Yeah, you're right.
Yes, sir. Honorable management members, principal, head of the department, my dear colleagues, faculty from other institutions, student community, a very good afternoon to one and all. I'm deeply honored for having been given this opportunity to propose vote of thanks on this occasion of valid function of 3-day webinar on advances in thermal sciences and fluid flows. First, I would like to thank the management members of Matrici Education Society for giving an opportunity to organize this kind of webinar on this platform. And also, I would like to thank our principal, Dr. V. Ma'am, for granting permission to conduct the 3-day webinar. And I would like to thank our dynamic head of the department, Dr. M. Madhavi Ma'am, for encouraging and motivating us to organize this kind of programs. If you have studied internal combustion engines, then definitely you would have come across a name for Dr. V. Ganeshan, who is a well-known person around the globe and famous author of IC engines. Being such great personality, he was very humble and kind enough to readily accept our invitation to address the participants in his plenary lecture. A deep gratitude towards his profession, and we are grateful to have you in this inaugural session. From the management, principal, head of the department, and faculty, staff of our department, we are thankful to you, Ganeshan sir. We are very much thankful to you for your enlightenment lecture on the topic of recent advances in automotive engines. The second session was addressed by Dr. P. Ushastri ma'am, professor in the Department of Mechanical Engineering, Usman University. She enlightened us on the topic of CFD analysis for thermal fluid flows, and we are very much enlightened in the topic what you have delivered to us. And thank you, ma'am, for accepting the invitation and delivering a wonderful lecture. The second day started with the Dr. K. Aditya, who enlightened us on a lean premix combustion in gas turbines, who is our alumni of our MVSR. A deep thank you for your wonderful presentation, Aditya. And the next session was delivered by Dr. Uma Maheshwar sir on the topic of mathematical modeling of fluid flows. It's very difficult to understand the mathematics behind the fluid flows, but the way he was so to understand the mathematical, so he was so kind enough to present the topic from basic level. So there are some participants also who requested us to conduct a full day program also. That shows how brilliantly he delivered the lecture. So we are very much thankful to Uma Mishra sir for the wonderful presentation. The next presentation was given by our alumni, Dr. M.V. Vamshi. He presented his session in a very systematic way and enlightened in the area of spray coatings. I would like to thank him for spending his valuable time, though it was late night at Canada. With a charming face, he presented the entire session. Thank you, Mr. Unshi. And our the dynamic convener, Dr. G.S. Sharma sir, for taking pain and organizing. Apart from organizing, he presented himself a session, so that was very wonderful, and it's really motivating for us, sir. And at last, I would like to thank the coordinators of ATS and FF team, Mr. B. Ravikumar sir, Mr. M. Ravikumar, Mr. Yogi Manas, Mr. Bhargav Chandra, and Suman Raju for putting their efforts to make this webinar a grand success. And I would like to thank faculty and staff of MET for supporting us in all aspects for organizing this program. Also, would like to thank head of the departments of various departments of MVSR EC for their encouraging and support. And I would like to thank my friend Mr. B. Venkatramana, who is assistant professor in the CSC department, and his team for helping out to telecast this 3-day webinar live on YouTube. Very much thankful to Mr. B. Venkatramana. And last but not least, I would like to thank all the participants, students, for spending their valuable time and listening to us for these 3 days, spending their valuable times and giving an opportunity to deliver a good sessions also. Thank you, one and all.
Thank you, Ravikumar. Dear participants, thank you very much. Please fill the feedback form and you will get your certificates within very short time. Very short time you will be getting your certificates. Thank you very much.